The geometry of most practical machining operations is somewhat complex. A simplified model of machining is available that neglects many of the geometric complexities, yet it describes the mechanics of the process quite well. This model is called the orthogonal cutting model. Although the actual machining process is three-dimensional, the orthogonal model has only two dimensions that play an active role in the analysis. The orthogonal cutting uses a wedge-shaped tool. The cutting edge is perpendicular to the direction of the cutting speed. The tool is forced into the material, and the chip formed by the shear deformation along a plane called the shear plane. The shear plane is oriented with the angle phi with the surface of the work. The sharp cutting edge of the tool, thus failure of the material occurs, resulting in the separation of the chip from the parent material. Along the shear plane, where the bulk mechanical energy is consumed in the machining, the material is plastically deformed. The tool in the orthogonal cutting has only two elements of the geometry. First, the rake angle, and second, the clearance angle. The rake angle alpha determines the direction of the chip follows as is going to be formed for the work part. And the clearance angle provides a small clearance between the tool flank and the newly generated work surface. During the cutting edge of the tool is positioned a certain distance below the original work surface. This corresponding to the thickness of the chip prior to the chip formation. As the chip is formed along the shear plane, the thickness will increase to the new value. Usually, the thickness of the chip after the separation is more than the thickness of the chip pre-separation. In addition to TO, the orthogonal cut has a width dimension W, even though that this dimension does not contribute much in the analysis in the orthogonal cutting. The ratio of the TO to TC is called the chip thickness ratio, or simply the chip ratio R. Since the chip thickness after the cutting is always greater than the corresponding thickness before the cutting, the chip ratio will always going to be less than 1. The geometry of the orthogonal cutting model allows us to establish an important relationship between the chip thickness ratio, the rake angle, and the shear plane angle. Shear strain that occurs along the shear plane can be estimated by further analysis. There is a differences between the orthogonal model and the actual machining processes. First, the shear deformation process does not occur along a plane, but within a zone if the shearing were to take place across the plane of the zero thickness. It will imply that the shearing actions must occur instantaneously as it passes through the plane, rather than over some finite time period. For the material to behave in an elastic way, the shear deformation must occur within the thin shear zone. In addition to the shear deformation that occurs in the shear zone, Another shearing action occurs in the chip after it has been formed. This additional shear, referred as a secondary shear, to distinguish it from the primary shear. The secondary shear results from the friction between the chip and the tool as the chip slides along the rake face of the tool. Its effects increases with the increased friction between the tool and the chip. The formation of the chip depends on the type of the materials being machined and the cutting conditions of the operation. There are four basic types of the chip can be distinguished. The first type is the discontinuous chip, where relatively brittle material, like the cast iron, are machined at low cutting speeds. The chips often form into separate segments. This tends to impart an irregular textures to the machine surface. High tool chip friction and a large feed and depth of the cut will promote the formation of this chip type. When ductile work materials are cut at high speed and relatively small feeds and depth, long continuous chips are formed. A good surface finish typically results when this chip type is formed. A sharp cutting edge on the tool and a low tool chip friction encourage the formation of the continuous chips. Long, continuous chips, as in the turning, can cause a problem with regards to the chip disposal and or the tangling about the tool. To solve these problems, turning tools are often equipped with the chip breakers. When machining ductile materials at low to medium cutting speeds, friction between the tool and the chip will tend to cause a portion of the work material to adhere to the rake face of the tool near the cutting edge. This formation is called the built-up edge. The formation of the built-up edge is cyclic. It forms and grows, then becomes unstable and breaks off. Much of the detached built-up edges is carried away with the chip, sometimes taking a portion of the tool rake face with it, which reduces the life of the cutting tool. Portion of the detached built-up edges are not carried off with the chip become embedded in the newly created work surface, and this causing the surface to become rough. The serrated chips are semi-continuous in the sense that they possess the sawtooth appearance that is produced by the cyclic chip formation of alternating high shear strain followed by the low shear strain. This fourth type of the chips is the most closely associated with the certain difficult to machine metals such as titanium alloys or the nickel-based silver alloys, and this stands still when they are machined at a higher cutting speed. However, the phenomenon is also found with more common works metals like the steel when they are cut at high speed. Several forces can be defined relative to the orthogonal cutting model. Based on these forces, the shear stress, the coefficient of friction, and a certain other relationship can be defined. Consider the forces acting on the chip during the orthogonal cutting. The forces applied against the chip by the tool can be separated into two mutually perpendicular components, the friction force and the normal force to the friction force. The friction force F is the frictional force resistance to the flow of the chip along the ring face of the tool. The normal force to the friction N is perpendicular to the friction force. The friction force and the normal force can be added vectorially to form the resultant force R, which is oriented at the angle beta and is called the friction angle. In addition to the tool forces acting on the chip, there are two forces components applied by the workpiece on the chip, shear force and the normal force to the shear. The shear force Fs is the force that causes the shear deformation to occur in the shear plane. And the normal shear to the shear force Fn is perpendicular to the shear force. The vector addition of these two forces will yield in the resultant force R prime. In order for the forces to acting on the chip in balance, the resultants R prime and R must be equal in magnitude and opposite in direction, and collinears with the resultant R. By using these forces components, we can find the coefficient of friction between the tool and the chip. Also, we can find the friction angle related to the coefficient of friction by using the following formula. The shear stress represents the level of the stress required to perform the machining operation. Therefore, this stress is equal to the shear strength of the work material under the condition at which the cutting occurs. Based on the shear force, we can define the shear stress that acts along the shear plane between the work and the chip, where the area, AS, is the area of the shear plane. None of the four forces components, the F, the N, the Fn, and the Fs, can be directly measured in the machining operations, because the direction in which they are applied vary with the different tools, geometries, and cutting conditions. However, it is possible for the cutting tool to be instrumented using a force measuring device called the dynamometers, so that two additional force components acting against the tool can be directly measured, the cutting force and the thrust force. By using analytical equations, we can find the forces that cannot be measured. The shear plane angle phi value will minimize the energy required for the cutting process. Phi on the orthogonal cutting, as well as the 3D machining, is given by Eugene Merchant equation. The higher shear plane angle means a smaller shear plane, which means a lower shear force, cutting forces, power, and temperature. To increase shear plane angle, we need to increase the rake angle alpha or reduce the friction angle beta. A machining operation requires power. The cutting force in the production machining operation might exceed 1000 Newton. Typical cutting speeds are several hundred meters per minute. The products of the cutting force and the speed give the power required to perform the machining operations. In US customer units, the power traditionally expressed as the horsepower. The PC here is the cutting power, and the FC is the cutting force, and the V is the cutting speed. The gross power required to operate the machine tool is greater than the power delivered to the cutting process because of the mechanical losses in the motor and the drivetrain in the machine. These losses can be accounted for by the mechanical efficiency of the machine tool. The gross power of the machine can be calculated as a ratio between the cutting power divided by the efficiency of the machine tool. The value of the E is within the range of 90%. It's often useful to convert the power into the power per unit volume rate of the metal cut, and this is called unit power or the PU. The unit power is also as a specific energy U. The RMR is the material removal rate in the cubic millimeter per second, as can be found with the following formula. Approximately 98% of the energy in the machining is converted into heat, and about 2% is retained as the elastic energy in the chip. This can cause the temperature to be very high at the tool chip point. The high cutting temperature disadvantages are: first, it's going to reduce the tool life. Also, it's going to produce a whole chip that poses a safety hazard to the machine operator. At the same time, it can cause inaccuracies in the part dimensions due to the thermal expansion of the work material. Analytical methods derived by Nathan Cook from dimensional analysis using experimental data of the various work materials. Cook equation: find the temperature raise in the tool chip interface. Depth measurement experimental methods can be used to measure the temperature in the machining. K-trigger equation determines the speed-temperature relationship to be in the form of T is equal to the K multiplied by the V up to power M, where the T is the measured tool chip interface temperature and the V is the cutting speed.